Namaskaram. Today we are going to discuss surface integral. These are the solutions of last homework. In last session, we have seen that how to integrate along a curve C, oriented curve C. Okay. Suppose this is our sigma. So sigma denotes the surface. Suppose sigma is a surface and we have a function f, x, y, z on sigma because this sigma is a 3D surface. Okay. So corresponding to every point we have a function f, x, y, z on the sigma. And we have to integrate this function over this sigma. That's our problem. The procedure is similar to our line integral. First we subdivide the surface sigma into n small patches having area delta sk. Okay, so delta for k is equal to 1 to etc n. Okay, so delta sk is the area of the kth patch. Okay, so similarly delta s1, delta s2, etc. Suppose this subdivision contains n patches. Okay, and we choose an arbitrary point xk star, yk star, zk star from the kth patch. Okay, we choose an arbitrary point. All procedure are similar to line integral. Okay, so x1 star, y1 star, z1 star is the arbitrary point from the first patch, like that. Then we can define an infinite sum similar to line integral. This is the infinite sum. Limit n tends to infinity, sigma k is equal to 1 to n f of xk star, yk star, zk star, delta sk. So delta sk is the area of the kth patch. Okay, into function value at a particular point, an arbitrary point from the kth patch. Then take this sum and then take limit n tends to infinity. So whenever limit n tends to infinity, what happened? This size of this patches reduces to close to 0, very small. That's the idea. Okay, so this is the definition of surface integral. If this limit exists, then we denote this infinite sum as double integral over sigma, because here we integrate over this surface, a 3D surface. Okay, our surface with respect to ds. What is ds? ds stands for the area of the small patch. Okay, so here we integrate this fxyz on the surface sigma with respect to aerial element. Okay, that's the idea. Okay, and this integration has several applications. We will see how to find flux using surface integral. Another application of surface integral is to find area of a 3D surface. Suppose sigma is a 3D surface, then we can find the area of this 3D surface using surface integrals. How? My question, for what values of function, for which value function f, this sum gives the area? Yes, if you choose f as 1, then what happened? The area of this 3D surface sigma is approximately equal to sigma k is equal to 1 to n delta sk, because delta sk is the area of the kth patch. Okay, so we take the delta area of first patch plus area of the second patch plus etc. Okay, so if you take the sum of this n patches, area is approximately equal to this one. Okay, we exclude this edge patches. Okay, because this edge is not a full patch, so we exclude such patches. And it is clear that this area is better if you take n as large, isn't it? If n is very large, this area is better. So in limiting case, area equal to limit n tends to infinity, sigma k is equal to 1 to n delta sk gives the area. Okay, so it is clear that here the function value f is 1. So if we choose f as 1, then this infinite sum gives area of sigma. Okay, so what is the corresponding notation of integral? Integral is nothing, integral is double integral over sigma ds. So area of a 3D surface sigma is given by this infinite sum, and it is denoted by our notation is double integral over sigma 1 ds. Okay, so if we simply integrate over a surface sigma, then we get area. Okay, Okay. So next problem is how to evaluate this double integral over a surface. Okay, we know how to integrate a double integral in xy plane. Okay, so next we are going to introduce a simple formula for evaluating double integral as like our usual double integral. Okay, because we can't evaluate this double integral using this formula. This is a infinite sum. This is not easy to calculate for functions. Okay, so we have to find a simple formula for evaluating this double integral. Okay, this is the result. We can easily evaluate double integral using this result. So the result says that if sigma is a smooth parametric curve, smooth means differentiable curve, and parametric surface. What is parametric surface? So parametric surface means we have to convert x, y, z, everything in terms of two variables. They are called parameters. Okay. So r is equal to x is function of uv, and y is also a function of uv, z is also a function of uv. Okay. So this is the parameter representation of a surface. Okay. Then double integral over sigma fx y z ds is equal to double integral r. R is nothing. R is the region in uv plane. Okay. R is a region in uv plane or projection to the uv plane. You can think about it as a projection to the uv plane. And f of first of all we convert everything in terms of u and v, everything in terms of parameter value, and it is determinant of or modulus of, sorry, this is modulus of dou r by dou u cross dou r by dou v. There are two vectors. R is a vector and dou r by dou u and dou r by dou v are vectors. You take the cross product of two vectors, then take the modulus into dA. So now this is like an ordinary double integral, because only difference is this double integral takes place in the uv plane. That's the difference. Okay, I'm not going to the details of this formula, because in our syllabus we have to discuss only three special cases of this formula. Okay, we will see that. Okay, the parametric surface, for example, we consider the surface x square plus y square plus z square equal to 4. This is the Cartesian form of the 3D surface or sphere. We know that what is x square plus y square plus z square equal to 4. It's a sphere with the radius 2. Okay, it's a 3D surface. This is the Cartesian form. And what is the corresponding parametric form? Okay, here these three formulas give the parametric form of the surface. Okay, now everything is in terms of two variables. Okay, instead of uv, here we take theta and phi, that's all. Okay, so x is equal to 2 into cos theta sin phi, and y is equal to sin theta sin phi, z is equal to 2 cos phi. Here 2 is the radius of this sphere. Okay, so it is clear that x, y, z, everything in terms of two parameters theta and phi. This is the idea of parametric representation of a curve. Okay. Okay, this is the first special case. Our surface sigma is of the form z is equal to gxy. Okay, then we can evaluate this surface integral using this formula. Okay, this is nothing. This is our modulus of dou r by dou u cross dou r by dou v. Okay, I will explain this. This is very easy, because what is our parametric form of the surface? Because here it is clear that already z is in terms of x and y. So we can choose x and y are the parameters. Okay, so what is the parametric representation of the surface? That is r is equal to xi plus yj plus g of xy k. So this is the parameter representation. Okay, no need to convert x and y in terms of u and v. Okay, we can take this as a parametric form. Only thing is here the parameters are x and y. Now everything is in terms of x and y. X is already in x, and y is in terms of x and y. G is z is also in terms of x and y. Okay, so in our formula we have to take dou r by dou u and dou r by dou v. And what is dou r by? So we have to find dou r by dou x, not dou r by dou u. Here our u is x. So what is dou r by dou u? That is I plus 0 j plus dou g by dou x k, isn't it? And similarly, what is dou r by dou y? That is 0 plus j plus dou g by dou y k. Okay, so these are the derivative. Next we have to find the modulus. What is modulus of? Okay, next we have to find the cross product. Then after that we have to take. After that we will take modulus. Okay. So what is dou r by dou x cross dou r by dou y? It's a determinant I, j, k. What is dou r by dou x? The coefficient corresponding to the dou r by dou x is 1, 0, dou g by dou x, and the coefficients corresponding to this one is 0, 1, dou g by dou y. Okay, so by expanding this determinant, if you take the if you expand this using the first column, that is I think better, because the one time is 0. So this become then minus dou g by dou x I minus dou g by dou y j plus k. Okay, anyway, you can expand this any order, no problem. You get its determinant is like this. Okay, so this is the cross product. Next we have to find the modulus. It's clear that its modulus value is square root of dou g by dou x square plus, okay, its modulus value is square root of dou g by dou x square plus dou g by dou y square plus 1 square. Okay, and what about dou g by dou x? Dou g by dou x is same as dou z by dou x, isn't it? Because z is equal to g. So we can replace this dou g by dou x by dou z by dou x, and this is by dou z by dou y, and plus 1 square is 1 dA. Now it is clear that this integration takes place on the xy plane, because our u and v are x and y itself. Okay, so this r is the projection of the surface to the xy plane. Okay, so this is the idea of evaluating this double integral. Similarly, we can develop other two formulas. Second one is, if sigma is a surface of the form y is equal to gxz, then this is the corresponding formula for evaluating the surface integral. Similarly, we have one more formula. If surface is of the form x is equal to gyz, then this is the evaluating formula for this surface integral. Okay, so all are similar to first one. Okay, first problem. Evaluate the surface integral double integral over sigma x z ds, where sigma is the part of the plane x plus y plus z equal to 1 that lies in the first octet. Okay, so this is the geometry of this surface. We know that x plus y plus z equal to 1 passing through 1, 0, 0, 0, 1, 1, and 0, 1, 0, and 0, 0, 1. Okay, these are the 3 points. So we know how to plot the surface, and we have to consider the portion corresponding to the first octet. So it's like a triangular portion on the first octet. So we have to integrate the function. Okay, our function fxy z is equal to xz. So this function is defined on this surface sigma. Okay, function defined on this surface sigma. You choose a point from this one, and there is a function at that point, like that. Okay, so we have to integrate this function on the sigma. We know how to evaluate the surface integral. So it is clear that our surface is x plus y plus z equal to 1. So this is of the form z is equal to 1 minus x minus y. Okay, it is clear that z is of the form a function of xy. So we can use our first formula. So what is our first formula? To use the first formula, we have to compute dou z by dou x and dou z by dou y. And what is dou z by dou x? Dou z by dou x is minus 1, and this is also minus 1. Okay, so we can directly write the formula. Double integral over sigma x z ds is equal to double integral over r. R is the projection of the surface sigma to the xy plane. Then next we have to convert everything in terms of the parameter value. Now here our parameters are x and y. So x is already allowed, no problem. So we have to convert z in terms of x and y. So what is z? Z is equal to 1 minus x minus y. Okay. The next one is square root of dou z by dou x square plus, that is minus 1 square plus minus 1 square plus 1. So this is the term dA. Okay. Now this is our ordinary double integral. We have to integrate this function on the region R. R is a projection of the surface to the xy plane. So next question, what is the projection? What about the projection of this triangular surface to xy plane? So it is clear that this triangle is the projection. The vertices are this 0 0 and this is 1 0 and this is 0 1. Okay, so we have to integrate in two-dimension plane. The coordinates are 0 0 1 0 and 0 1. Okay, in 2D plane. So we have to integrate this function over this triangular region. Okay, so I redraw this figure. Yeah, this is the figure. This is our x-axis. This is y-axis. In this 3D figure, the x-axis in this direction. This is our y-axis. Okay, so x value is 1 0 and at y the intercept is 0 1. So we have to. This is our region R. This is our region R. So we have to integrate along this region R. So either you can take the vertical strip or horizontal strip, which are no problem. So first of all, I am going to integrate this by taking a vertical strip. Okay, in this vertical strip, what is our value? Y. Here y value is always 0. And what about the y value on this edge? Or what is the equation of this edge? First of all, we have to find this equation of edge. This edge means equation of this straight line. What is the equation of this straight line? Okay, it is clear that this straight line is also a part of this plane, isn't it? But only difference is on the straight line z value 0. Clear? So when z equal to 0, we get x plus y equal to 1. So this is the equation of the straight line. So equation of this straight line is x plus y is equal to 1. X plus y is equal to 1. So what is y value? Y value is nothing. Y is equal to 1 minus x. So y is always starting from 0 to 1 minus x. And to cover this region, x should varying from 0 to 1. Then only this strip cover this triangular region. So now everything is clear. So we can set this integral as like this. So double integral. So range of y is 0 to 1 minus x. And range of x is 0 to 1. And this term become like this 0 to 1, 0 to 1 minus x minus x square minus xy into root 3. This is root 3. And what is the order of integration? Yes. First of all, we have to integrate with respect to y because this is the limit of y. So this is dy dx. Now everything is ready. We can simply evaluate this double integral as our usual integration. Okay. Okay, after the first integration with respect to y, this is like this. And our lower limit is 0, upper limit is 1 minus x. After the substitution of these limits to y, we get like this. Next, we have to integrate this expression with respect to x. Okay. Then after this integration, we get root 3 times x square by 4 minus x cube by 3 plus x raised to 4 by 8. And limits are 0 to 1. After substituting this upper limit and lower limit, and by simplification, this expression become square root of 3 by 24. So this is the value of this surface integral. Okay. This root 3 by 24. Next problem. Evaluate the surface integral double integral over sigma y square z square ds, where sigma is the part of the cone z is equal to square root of x square plus y square that lies between the planes z equal to 1 and z equal to 2. So we know cone is like this, z is equal to say circular cone. Cone is like z is equal to square root of x square plus y square. And we cut this cone using the plane z is equal to 1. We cut this one z equal to 1. Okay, this is our z equal to 1. And this is our z equal to 2. Then we get a portion like this. So this is the corresponding portion. So our surface sigma is this surface. This circular shaped surface is our sigma. Okay, this is our sigma. So we have a function y square z square. So our fx y z is equal to y square z square. This function is defined on this surface sigma, this curved surface sigma. Okay, we have to integrate this function over the surface sigma using our surface integral. Okay, and also it is clear that our surface is already in the form z is equal to gxy. So we can use our first formula for evaluating the surface integral. Okay. So we have to find the derivative with respect to x and y. So what is dou z by dou x? That is 1 by 2 times square root of x square plus y square into derivative of inside, that is 2x. So this becomes x by square root of x square plus y square. And similarly, we can find dou z by dou y. And similar are given 1 by 2 root of 2 times square root of x square plus y square into 2y. So ultimately this becomes y by square root of x square plus y square. Okay. So these are the partial derivatives. Then next we have to compute square root of dou r by dou x. Sorry, not the dou r by. So square root of dou z by dou x square plus dou z by dou y square plus 1. That is equal to the square of this term, that is x square by x square plus y square, plus square of this term, that is y square by x square plus y square plus 1. Okay. Then by taking the LCM, this become square root of, by taking sum of first two. If we take the sum of first two, so this become x square plus y square by x square plus y square plus 1. So this is equal to square root of 1 plus 1, that's equal to square root of 2. Okay, so this term becomes square root of 2. Next we have to find the this surface integral using normal double integration. Okay, so this become double integral over sigma y square z square ds. So next we are going to set up this double integral as a normal integration. Okay, so double integral over the region R is the projection of this region, and we have to convert everything in terms of the parameters. Here parameters are x and y, so y square is allowed, so y square into, what about z square? Z is already in terms of x and y, so z square is nothing, x square plus y square. So this is x square plus y square into this term, this is square root of 2 into dA. So our surface integral now is a like our normal integration. So the only thing is we have to integrate this integration over the region R. What is region R? R is the projection of this surface, this slanted surface. Okay, it is clear that its projection is like an annulus, a region between two circles. Okay, so we have to find the radius of this circle and radius of the circle. Then we get an annulus region. Then we have to integrate over that region. Okay, that is our procedure. Okay, what is the equation of this inner circle? Okay, to find the inner circle, it is clear that this inner circle is the projection of this circular region. It's a projection of the circular region. So what about the equation corresponding to this intersection? So when z equal to 1, what happened? Okay, our slanted surface cone is z is equal to square root of x square plus y square. When z equal to 1, this become 1 is equal to square root of x square plus y square. That means x square plus y square equal to 1. Okay, so the equation of this circle is same as x square plus y square equal to 1. In 3D, what about x square plus y square equal to 1? In 3D, it is a cylinder. Okay, cylinder like this. But we have to find only the equation of the circle on this xy plane. So that is our x square plus y square equal. So equation of this inner circle is x square plus y square equal to 1. And similarly, what about the equation of the outer circle? To find the equation of outer circle, we have to simply substitute z equal to 2 on this cone. So when z equal to 2, this becomes 2 equal to square root of x square plus y square. This gives 4 equal to x square plus y square. So x square plus y square equal to 4 is the equation of the outer circle. So this is nothing, is a circle with the center origin and radius 2. Okay, now it is clear which is the annulus, which is the region R. It is the annulus region bounded by two circles, x square plus y square equal to 1 and x square plus y square equal to 4. Okay. Okay, I just redraw the projection surface R like this. So this is our x axis and this is our y axis. Okay, so we have to integrate over this region R. This is our region R. Either you can evaluate this is in Cartesian form. I think better we use polar form to evaluate this double integral. Okay, in polar form we know that what is x? X is equal to r cos theta and y is equal to r sin theta. These are the polar representation. In polar representation, what about dA? dA is nothing, r dr d theta. Okay, so our task is to find what is the range of r and what is the range of theta. Okay, and what is the range of r? What is range of R? Yeah, to cover this region, R should varying from, this is R is starting from 0. This is the value R equal to 1. So R should varying from 1 to 2. Okay, R should varying from 1 to 2. Okay, then to cover this entire shade region, this strip should move from this point to this point. Okay, to cover this region, theta should varying from 0 to 2 pi. Yes, so R is varying from, R is varying from uh, 1 to 2, and theta is varying from 0 to 2 pi. So this is the setup of this double integral. Okay, then you can easily rewrite this integral using polar representation as like this. This is our square root of 2 by take outside into 0 to 2 pi and 1 to 2, range of r, range of theta. And what about y square? Y is r sine theta, so this become r square sine square theta. And next term is x square plus y square. We know that x square plus y square equal to r square, so r square into our dA. dA become r dr d theta. Okay, so this becomes square root of 2, 0 2 pi 1 to 2, and this is r raised to 5 sine square theta dr d theta. Next we are going to integrate this expression with respect to r. So this become r raised to 6 by 6. Okay, and we know that sine square theta is equal to 1 minus cos 2 theta by 2. Okay, then by substituting this formula and then integrate, we get 21 by root 2 theta by 2 minus sine 2 theta by 4 0 to 2 pi. On simplification, we get 21 pi by square root of 2. So this is the value of this surface integral. Okay, yes, 21 pi by square root of 2. That's it. So this is your homework for this session. Thank you.